Good morning, students. Welcome to physics class. Today we are going to start with a new lesson, fourth chapter, which is electromagnetic induction and alternating current. Yes. So here, first, the terms which we have to know is magnetic flux. So what is meant by a magnetic flux is it is nothing but the number of lines. Okay. So whenever you consider this to be the magnetic field, over this how many number of lines is crossing through a closed surface. So we are considering any closed surface, in that how many number of lines is passing, that is called as a magnetic flux. So magnetic flux through an area A in the magnetic field is defined as the number of magnetic field lines passing through that area normally. Okay, so magnetic flux is nothing but it is just the number of lines. So magnetic flux nala enna solluvom, number of lines. Okay, and it is given by the formula phi is equal to integral b dot dA. So whenever we are having with a dot product, we'll be writing with cos. Okay, whenever we are having with a cross product, we'll be writing with the term sine, is it not? So here we are having with a dot, so we are writing with cos theta. So b a into cos theta. Yes, clear? So this is the formula for magnetic flux. So what is the definition for magnetic flux is? Magnetic flux through an area A is defined as the number of magnetic field lines crossing through the area. So phi is equal to integral of b dot dA, which is equal to BA into cos theta. Okay, so this is a formula for magnetic flux. Clear? Now if we consider this to be the magnetic field lines, so this is a closed area. In this closed area, these are the magnetic field lines which are moving. Okay, suppose if that surface and the field, if they are perpendicular, what happens is it does not make any angle, is not? So here when you see, this is being tilted, and so it makes with an angle theta here, but here there is no angle. Okay, and so we are considering theta to be equal to 0. So when you substitute theta to be equal to 0 in the equation is phi is equal to BA into cos theta. So instead of cos, we are writing as 0, and so cos 0 value is 1. So we are getting the equation as phi is equal to B into A. So this gives the formula for magnetic flux. Phi is equal to B into A. Clear with the formula? Okay. Then next is we are going to see with the unit. The SI unit of magnetic flux is Tm square. Okay. The other unit we can say is Weber or WB. Weber is represented as WB. Okay, so this flux has two units. One is Tm square and WB. So we can say that 1 WB is also equal to 1 Tm square. Clear? So this is about the magnetic flux. The unit is what? Tm square or Weber. Clear? Next is we are going to see with what are the Faradays laws of electromagnetic induction. So considering with this Faradays law, whenever the magnetic flux linked with a closed coil changes, so when it is changing means, suppose if this is a magnetic flux first, okay, then the magnetic flux is being changed like this. So when you count the numbers here and when you count here, there is a change, is not? Here there are only 2 numbers and here we have the 5 numbers. Yes, and when it changes in such a way that an EMF is induced. So whenever the magnetic flux changes, so lines change ஆச்சு அப்படினால என்ன ஆகும்? EMF வந்து induced ஆகிடும். So what is meant by EMF is nothing but it is an electromotive force. Okay, so electromotive force is induced. அதனால என்ன ஆகும்? Electric current flows in the circuit. Okay, so because of the change in the magnetic flux, okay, there is a EMF. EMF nala enagum? Current flow agum. That current is called as a induced current. Okay, and the EMF which is produced is called as a induced EMF, and this full phenomena is called as a electromagnetic induction. Clear? So whenever there is a magnetic flux linked with a closed coil changes, so flux change ஆகும்போது என்ன produce ஆகுது EMF. When the EMF is induced, there is always current. அந்த கரண்ட்டுக்கு பேர் தான் இது induced current. அப்படி flow ஆகுற EMFக்கு பேர் தான் இது induced EMF. This full phenomenon is called as a electromagnetic induction. Clear with this concept? Okay. So next is we are going to see with the laws. So there are two laws in this, first law as well as second law. So first law is whenever the magnetic flux linked with a closed circuit changes, an EMF is induced. So we have seen this already, is it not? So flux change ஆச்சு அப்படினால என்ன ஆகும்? EMF வந்து induced ஆகிடும். Okay. Then second one is the magnitude of the induced EMF is equal to the time rate of change of magnetic flux. Okay, so magnitude of induced EMF is given by E. Okay, that is equal to time rate of change of, so that is given by d divided by dt of magnetic flux. So magnetic flux is given by phi. Okay, so E is equal to d phi divided by dt. So when you know with this equation, you can easily write with this law. Okay, so what is it is E is what? The magnitude of induced EMF. So magnitude of induced EMF is equal to the, this is said as time rate of change of. Okay, so time rate of change of phi is said to be the magnetic flux linked with the circuit. Clear? So these are the Faraday's law. So what is Faraday's first law is whenever the magnetic flux linked with a closed circuit changes, an EMF is induced in the circuit. Second law is the magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. Clear? Then next is we have the equation for this. If the magnetic flux, I told you already, E is said to be the EMF and phi is a flux, so it is given by E is equal to minus d phi by dt. So why we are writing with a minus sign here is because it gives the direction of induced current. Why we are writing with a minus sign? Because it is an induced current. Induced current always flows in the opposite direction. So here we are writing with a minus sign. Clear? Next, Lenz's law. So Lenz's law, it states that the direction of the induced current is such that it always opposes the cause responsible for the production. So what is meant by this is, if suppose this side is the direction of production, so production is what? How the current is produced. Okay, so this side is the direction of production, then the direction of induced current is in the opposite direction. So direction of induced current, it is always opposes the cause responsible for its production. Clear? So Lenz's law states that here is the direction of what? Induced current. So direction of induced current is such that it is always opposite to the cause responsible for its production. Clear? So this is a very important one, which is Lenz's law. It states that the direction of induced current is such that it always opposes the cause responsible for its production. Clear? So next we have Fleming's right hand rule. So this diagram denotes, which you know already, which you have seen already in the Fleming's left hand rule, is it not? So we have to stretch the thumb, forefinger and the middle finger. Okay, so this diagram is given for the left hand. Okay, because see here, forefinger points in the direction of field, then middle finger points in the direction of current and thumb points in the direction of force. Okay, so this is for the left hand, but here we are going to see with the right hand, same as this, but the only difference is here the forefinger points in the direction of magnetic field and middle finger points in the direction of induced current. Okay, and thumb points in the direction of motion of conductor. Okay, so this is a only difference. Okay, so this two will differ. Here we are having with the current, but right hand will write it as induced current. Here we are writing with the force, but here we will be writing with the motion of conductor. Okay, so that is the difference between the left hand and the right hand rule. Clear? So the statement of Fleming's right hand rule is thumb, index finger and the middle finger of the right hand are stretched so that they are mutually perpendicular. So all these three should be in the perpendicular direction. So if they are perpendicular, then the index finger, so first we are saying with the index finger, that points in the direction of magnetic field. As I have told you already, index finger points in the direction of magnetic field, thumb indicates the motion of conductor and the middle finger points in the direction of induced current. Okay, so you have to know the difference between the Fleming's right hand and also the left hand. Okay, in left hand we have already seen that index finger points in the direction of magnetic field, thumb points in the direction of force on a conductor, and the middle finger points in the direction of current, is it not? So this is what we have seen in the Fleming's left hand rule. So the only difference is here we are writing with the motion, and for current we are writing with the induced current. Clear? This is about the right hand rule. Yes.